In this first example, you're just asked to match some general forms of log and exponential equations with some general graphs. And we'll start with a. So a is the function f of x equals log base b of x, where b is greater than 1. So this is a log function, so we can automatically get rid of this function here and this function here. And it looks like it's going to have to be one of these two functions because of their vertical asymptotes that are implied within the graphs. So with b being bigger than 1, this will be an increasing function. And so this will go with the red graph. For the second one, I think it becomes a little more clear because the only other log function we have is this one right here. So this function will be paired up with the white graph. And now these last two are exponential functions, and you know that these other two graphs are exponential functions because it looks like there's a horizontal asymptote here. So what we will do is evaluate a little further here. When the base is bigger than 1, that means the function is increasing. So like this graph right here, so part C will get matched up with this graph, which leaves part D being matched up with this graph. And that's because this is an exponential graph here. You can tell by the horizontal asymptote. And the base is less than 1, which means it'll be a decreasing function left to right. In this exercise, you are simply asked to graph the following function. I only need 3 points to make an accurate graph of an exponential function. And be sure to draw and label any asymptotes. And you're also asked to find the domain and range. So right away, I would just like to get the domain out of the way. Since this is an exponential equation, I know the domain will be negative infinity to infinity, or, if you like, all real numbers. So I will leave a little space here for the range. It'll be easier to figure out what the range is after we look at the graph. So in order to make the graph for this, I'm going to make what I call the parent table. And so I'm going to call this table x is over here and g of x is over here. And these three numbers are what I'm going to use every time: -1, 0, and 1. And now how do I know what the y values are for the parent table? I know always that 0 will be paired up with 1. And what do I mean by the parent table? I'm just looking at this little piece right here, the base and the x in the exponent, and that is it. So when I just look at the base and the exponent, I get 0, 1, 1 and the base will always be paired up, and -1 and the reciprocal of the base, or flip the base, will be paired up. So here's my parent table. Off to the side, I'm just going to write down a couple things here, and those being the transformations. This +4 means the graph is moved up 4 units. And the little symbol in front, this negative here, tells you to reflect over the x-axis. Now, if you're moving up 4 units, that means you add 4 to the y values. And if you're reflecting over the x-axis, that means you'll multiply the y values by -1. And with this, I'm going to apply these transformations to this table. So if I multiply 3 by -1 and then add 4, I get a new value of 1. -3 times 1 is -3. 3 times -1 is -3, plus 4 is 1. On this next one, if I multiply 1 by -1 and then add 4, I get 3. And finally, if I multiply 1/3 by -1 and then add 4, I will get 3 2/3. Now I have this table of new values. -1, 0, and 1 are still my x values. There were no x transformations here. But there were a couple transformations to my y's, and these are my new y values. So they're still paired up in the same row. So I'll be having -1, 1 is one of my points, 0, 3 as another point, and 1 and 3 2/3 as my third point. But before I do that, I want to come back up here and look. If there's a number hanging out back here on an exponential function like this +4, that tells me automatically that I will have my horizontal asymptote at y equals 4. So right about here will be my horizontal asymptote. And now that I have my horizontal asymptote there, I want to make sure that I get my graph down. So -1, 1 is this point right here. 0, 3 is this point right here. And 1 and 3 2/3 is about that point right there. So I'm going to label these -1, 1. This point is 0, 3. This point is 1, 3 2/3. It's always good to label the points, that way everybody knows where they are. I'm just going to come in and draw my graph like this. And there's my graph. So we have the domain, we have the asymptote. The only other thing we needed was the range. And now by looking at this graph goes down forever, so the range will start at -infinity, and it goes all the way up and gets really, really, really close to the horizontal asymptote, which is 4. And I'm going to put that in red here, just so you can see that the horizontal asymptote will be part of the range. It is a y value, a y equals, it's a horizontal line, so it makes sense that it is part of the range. In this example, we will be asked to write things into from exponential form into log form. So here's the first example, 3 to the 2x equals 10. Well, since I know I'm going to be writing it as a log, I need to write log. You have to have a log in there somewhere. So a couple things is that the base of the exponential piece, this 3 here, will match the base of the log. So I know this will be a log base 3, and that the log is always equal to an exponent. So this log will be equal to the exponent, which is 2x. That's the entire thing in the entire expression in the exponent. And what's left over is this 10, and whatever's left over is what goes inside the log. So there is the first switch around. Another one that I want to do is part C, and that is because we have base e to the x power equals y plus 9. And already, one thing that you'll want to notice before you switch over to log form is to have the exponential piece isolated, so the base and the exponent. And we have that here. There's a base e and the exponent x. Now, since this base is e, that means you'll be using a natural log. So I will write natural log. It's still a log, but it's a natural log. So we have a slightly different notation for this. So here it is. It's natural log. Let's see. And that has a base e down here. We don't write the base e, but it's there. And it's implied. So we won't write it, but it is there. Just remember that as you're going through extra examples or an exam or a quiz in your future. But we do know that this log will equal the exponent, in this case, x. And whatever's left on the other side, y plus 9 will go in its own set of parentheses. So we have these answers. And then the last one I want to do right here is 3/4 to the x minus 5 equals 91. Now this is exactly the same process as the other ones. I know this is going to be a log. It doesn't have an e for a base, so I know it's going to be log log. The base is 3/4, and that's fine. Remember, bases just have to be positive numbers and not equal to 1. So we've got that there. This will equal x minus 5, and the 91 will be the argument. On this slide, we will be changing from logs to exponential form. Again, I'm just going to do a couple of these. One reason I want to do a couple of these is just to remind you that if you see ln, that means there's a base of e. So when we look at this and we're trying to rewrite an exponential form, the base will match the base of the exponential part. So I know e is my base, so e will be the base of my exponential piece. And you need to remember that the log is always equal to an exponent, in this case 7. So the exponent goes on the base. So e to the 7th power equals, so we've taken care of the base, we've taken care of the 7. What's left? X plus 6. And that is the exponential form of this particular log equation. Now to continue that idea, why I particularly chose D is that when you look down here, this is log, but there is no base. And if there is no base, that means the base is 10. And you can write it in there if you want to, just to make sure you remember that it's 10. But now the base of the log and the base of the exponential piece will match. So that takes care of the 10. This part over here, whatever the log is equal to, that is the exponent, r plus t. And whatever's left, so we've taken care of that. Whatever's left is this s. That's what the log is, what the exponential piece is equal to. So there we have 10 to the r plus t equals s. All right, on this slide, we will be asked to find the exact value of each given expression. So in this first one, part A over here, this is log base 3 of 1 over 27. And we can surely figure this out if the base of the argument, what's inside here, matches the base of the log. So this is going to be our clue. We want the base to be 3. We want the base of the argument to be 3. So let's see. This will be log base 3 of 3 to some power gives me 1 over 27. Well, in order to figure out what this is, we first need to notice that we're trying to get from 3 to 27 by using an exponent. And so 3 to the 3rd power definitely gives me 27. So in my answer up here, or my exponent up here, I'm going to at least write a 3. But what you also need to notice is that this 27 is in the bottom of a fraction. And this 3 that's here is not in the bottom of a fraction. So to get a number from the top of the fraction to the bottom, the exponent needs to be negative. Now, as long as we have the similar base inside the argument and the log, if they match, the answer here will just be the exponent. So the answer for part A here is negative 3. Now for part B, you can see log base B of the 4th root of B. And that's great and everything, but what the heck is the 4th root of B? What does that mean? Well, we have the same base. This is B and this is B, right? The base of the argument is B, base of the log is B. What's the exponent here in the argument? Well, I don't know, but I can try rewriting this. Log base B of B. Whatever exponent is on B on the inside, like this right here, 1st power, the exponent will go on the top. And whatever number is in the root here will go in the bottom of the exponent. So now we have log base b of b to the 1/4 power. So the answer here will be that exponent, 1/4 power. Now we're going to look at the flip of this. In part C, we have a log that's in the exponent. Instead of having something with an exponent inside of a log, we have a log that is in the exponent. Well, the base of the log is 2. The base of the whole exponential part is 2. It's almost like we just get to cross these out for free, cancel them away. And our answer here will be 59. Awesome. That's a lot easier than what I thought it was going to be. All right, in this next example, log base 6 of 0. This is basically asking you what power of 6 gives you 0. And it turns out this is impossible. We cannot raise 6 to a power to get 0. This is undefined. Another way to think of this is if you look at the argument that is inside the log here, this 0, if you go back and think about the domain of a log, as long as there are no transformations, starts at 0 and goes to infinity. But you'll notice right here, this left parenthesis here, we do not include 0. So remember, you can only have positive numbers inside the log. This is not a positive number, so it is therefore undefined. For this next one, however, we are trying to figure out what power of 1/9 equals 1. Well, I already said if we can have matching bases, the matching base of the log with the base of the argument, then we can just say that this equals the exponent. Any allowable base to the 0 power gives you 0. So this particular example, 1/9 to the 0 power, is the same thing as 1. So we can just move that exponent over here. For the next part G, it's noticing that the natural log is being used and that it has a base e. It's not written, but anytime you see ln, you can write that e down here. And since the base of the log and the base of the argument match up, we can just say that this simplifies down to the exponent, 23. And finally, in part I, it's the exact same thing. The base of the log matches the base of the exponent, so we can just say this is equal to that exponent. On this slide, we're going to talk about finding the domain of logarithmic functions. And you may recall that just on the last slide, I said we cannot find the log of 0. And that's because we know that the domain, or that the log can only have positive arguments. So since numbers have to be positive on the inside of the log, if we take the inside of the log and we set it to be bigger than 0, that guarantees us that the argument is positive. So if we can solve for x, then we can find the domain. So subtract 3 from both sides, and we have to say x is greater than -3. Well, since x is greater than -3, the interval notation will look like this. -3 and numbers to the right, all the way off to infinity. You can go ahead and practice part B on your own. I will let you know that the domain does start at 9/2 and goes off to infinity. Now with part C, I want to do part C so you can see recall one tiny little fact about inequalities, and that is if you take the argument and you set it to be bigger than 0 and you solve for x, and you subtract 1 from both sides. I will then divide this by -1, and that is your clue. Dividing by a negative tells you to flip the inequality sign. So I'm dividing by a negative. It's the fact that this number down here is negative. So this becomes x is less than 1. And if you're trying to change that into interval notation, it'll be this. Numbers less than 1 are to the left of 1, so -infinity to 1 will be the domain here.